Uh, so rigid body kinetics, number 16. Um, there's a mass of 50 kilograms. And then there's a force of 600 newtons applied to the cable at this angle that we don't know. Um, and when you first glance at it, you think you must have to know that angle. It turns out that you don't. And the reason is for any cable force coming over a pulley, the direction of the force is tangent to the circle. And the R vector, that's not R vector is perpendicular to it, or I guess that's what I would call in equations and stuff. This would be the rho vector. And so since these are 90 degrees from each other, that moment is always just equal to, and talking about the absolute value, it's always just going to be equal to the radius of the circle times the magnitude of the force. That's a perfectly safe assumption all the time, yeah. So the cable force is just always tangent to the circle. That's just how the cable comes off of a pulley. And that means it's perpendicular to that rho vector. And so you don't need to know the angle. Nope. Nope, not at all. You can just assume that. Any other parts of that question you'd like to see? Or just that? Okay. Any other homework questions? Yep. Oh, okay. 17A. So this is another one with a pulley hanging from the ceiling. And you have two masses. And for part A, we're assuming that the pulley doesn't have any mass. So for this one, we can just do a free body diagram of the 50. That's the weight is 50 times 9.81, 490.5. The force applied by the cable is up, and I'll call that T. And then the free body diagram of the 100. We have a weight force of 981. And since the pulley is massless, the cable force is the same magnitude everywhere, so this is also T. Yep, 70. So 688.6. And then you know that those acceleration vectors are equal and opposite. So you have one equation that says T minus 490.5 is equal to 50A, and you have another one that says T minus 688.6 is equal to negative 70A. After you write them out in vector form and everything. And then we can subtract this one. And we get 190, 196.2 is equal to 120A. Is that right? And then, so what do you get for A? Ooh, okay. Okay, that's true. I was surprised we were doing that part. Okay. It's accelerating downwards. All right, so in both cases, the acceleration of the mass, well, I'll do it for the 50. So let's say the acceleration of the 50 relative to the ground is equal to the acceleration of the 50 relative to the whatever elevator, plus the acceleration of the elevator relative to the ground. And this one is what's given as 0, negative 2. And relative to, it doesn't say it's an elevator, but whatever that vehicle is, what we know is that the acceleration of the 50 relative to the elevator is equal and opposite to the acceleration of the 100 relative to the elevator. We can write that as, I'll just write that as 0A, but 0A is not the total acceleration of the 50 relative to the ground, it's the acceleration of the 50 relative to the elevator, so that we can come up with that geometric relationship between them. Okay, so Newton's second law for the 50 says 0t plus 0, negative 490.5 is equal to 50 times the total acceleration, which isn't just 0A, it's 0A plus 0, negative 2. Okay, because you have to do it in an inertial coordinate system. So this is 0 and then A minus 2. And so we get this equation that says T minus 50A is equal to positive 490.5 minus 100, so 390.5. Just rearranging that. And then we're going to do the same thing with 100. A 100 question? Thank you. I think you should just let me do whatever problem I feel like doing and just be with that. Okay, so acceleration of the 70 relative to the ground is equal to the acceleration of the 70 relative to the elevator. plus the acceleration of the elevator relative to the ground. And again, this one is 0, -2. So Newton's second law for the 70 is 0t plus 0, -688.6 is equal to 70 times 0 for x. Then acceleration of the 70 relative to the elevator is 0, -a. So this is -a minus 2. And that gives us our second equation that says t plus 70a is equal to positive 6, so positive 588. 548. Oh, yeah, right. 0.6. And now we're solving for A. We can, I guess, subtract the first equation from the second equation, and we get the t's cancel. We have 120a is equal to 548.6 minus 390.5. $158.1, and then what's A equal to? 1.3 meters per second squared. So what would we get if this is accelerating down. If we had done it without the relative accelerations, I erased what I was about to do there, but what were we going to get? We were going to have 158.1. No, one. That must be 100. So basically, here's what I'm getting at. If that pulley was not accelerating, would we have gotten a larger magnitude of acceleration or a smaller magnitude? We would have gotten a bigger magnitude of acceleration because this was accelerating down. So accelerating down has the effect of decreasing the gravitational field. Accelerating against the gravitational field has the same effect as increasing the strength of the gravitational field. Any questions about that? Yep. That's not the total. Well, what does it ask for? What's the acceleration? For the total accelerations, this is the one where an observer inside the elevator would think this was the acceleration. If you want the total acceleration relative to the ground, then you just have to use the relative motion equation and add on the 0, -2 to that vector. Any other questions? Any other homework questions? Yep. Mm-hmm. Yeah. Mm-hmm. As long as the thickness is constant, you can do it all as areas. Yeah, they'd give you the same answer. If the thickness changes, the thickness into the page changes, then you have to use volume. You can't use area. Okay, so let me do my last example. I hope we can do this in this amount of time. So we've done rolling down an incline. We've done pulleys with mass. And the last one we want to do is the Pinewood Derby. Okay, so we're going to derive an expression for the acceleration of a Pinewood Derby car down an incline. And we're going to think about it as, so here's the car. We're not going to worry about air resistance or anything, so that shape is as good as any. The mass of the body of the car we're going to call 4 times big M. And then each wheel is going to have a radius R, a mass little m, and a moment of inertia IC. And the reason that I'm calling the mass of the body 4m is so I can just treat this problem as a single wheel with a single big mass m sitting on top of it. And we don't have to worry about all 4 of the wheels and its redundancy and everything. And then we have an incline theta. Okay, so first, like I said, we're just going to treat one wheel and 1/4 of the total top. And so we're just going to be dealing with a wheel of mass little m and a top part of mass big M. And I'll start with a free body diagram of the top. Yep. Yeah, that's right. No friction. All that stuff, the air resistance, the rolling resistance, the friction between the axle and the wheel, we just have to know some specifics about that, but it wouldn't be too much harder to add that in. Okay, so we have a weight force of big mg, and then we're going to use this coordinate system like you use for friction sliding problems, where the y-axis is pointing directly out of the surface, the x-axis is along the surface. And that's why I'm going to, for the force R, the reaction force with the pin, I'm going to draw it tilted. Since it's a pin joint connecting the top to the wheel, that's an unknown force, a force vector with an unknown direction and no couple. So let's see, I'm going to call this the force on the top by the wheel. And then Newton's second law says F, T, W, X, and Y plus mg sine theta negative big mg cosine theta is equal to the mass of the top times the acceleration. What axis is this going to accelerate along? X, yeah. So I'll write that as A0. And so we can think of this as two equations. FTWX minus big MA is equal to negative mg sine theta. And then we have FPWY is equal to positive big mg cosine theta. I'm not going to number these yet because we're going to see that some of these aren't going to help us go in the direction we want to go, and we can leave them out. And we're not dealing with any kind of rotation of the body, so I'm just going to treat that as a particle. And now we're going to go on to the wheel. Why did we even deal with the body? Why didn't we just, like, I think a lot of people would think, okay, let's just isolate the wheel and we'll just apply the weight of the body to the wheel at the center of the wheel and go from there. Well, this term right here is y. And this is one of the two reasons that doing statics before dynamics can cause some problems in your understanding of stuff. If this was a static case and there was no acceleration, the entire weight of the body would just be pushing down on the, would be applied to the axle, which would apply it to the wheel. And then FTWX would just be equal to that, the appropriate associated component of the weight. But since we have acceleration, that's not the case. And if you made that assumption, you'd get this wrong. Okay. So when two things are connected, if you think of the force the top thing is applying to the bottom thing as just being the weight of the top thing, that only works in a static case. If you have acceleration, that doesn't work. Okay, so now free body diagram of the wheel. Um, so we have a weight of little mg, and then wherever the wheel is in contact with the incline, this is making the incline look a lot steeper. Um, you have a normal force and a friction force. There has to be that friction force or it won't roll, it'll just slide. And I'm missing one more force. Yeah, right. So then there's also a force vector on the wheel by the top. And Newton's third law says that's equal to negative F on the top by the wheel. And we're doing that because we've already defined this variable FTW. We don't want to define a separate variable FWT if we know the relationship between. And then rho, force, moment. So first I'll do, well, this is a rigid body problem. So we have to think about whether this has a fixed point or not. Does a rolling wheel have a fixed point? Almost, but it doesn't. It does have a point where the velocity is equal to zero, but the acceleration is not zero. So we have to do all of this about the center of mass. Okay. So the about point is equal to the center of mass. And the moment of inertia about the center of mass is I sub c. That's already given. Okay, so I'll start with negative ftw. What's the rho vector? Zero. Um, force vector is negative ftwx, negative ftwy, and zero. And there's no cross product. And then the next one is the weight. Rho vector is zero again. The force is mg, little mg sine theta, negative little mg cosine theta, 0z, and then zero moment. And then the contact force I'm going to lump into a single vector. Those are happening at the same point, and if two forces are acting at the same point, you can always treat them as a single force vector. The rho vector for that one, we start at the center and go a distance r in the negative y direction. So this is 0, negative r, 0. The force vector is negative ff, positive n, 0. And so the moment is 0, 0, negative r, f, f. We need Newton's second law for this? Yes. So we have, the z components aren't going to give us anything, so I'll just do the x and y components. So negative f t w x, negative f t w y, plus mg sine theta, negative mg cosine theta, these are the little m's, plus negative ff normal is equal to, what's the acceleration? We have a massive little m. What's the acceleration of the center of the wheel? the center of mass of the wheel. Well, we've already defined a variable that tells us this. The center of the wheel is going to have the same acceleration as the top. And so we have to use A0 again. And this gives us two equations. Negative FTWX minus FF minus MA is equal to minus MG sine theta. And then the y equation says negative FTWY plus N is equal to positive mg cosine theta. And then the moment equation, the total moment, and we're just going to do we're only going to need the z component. Everything else is zero. We have a moment of negative RFF. And that's equal to the mass moment of inertia, I sub c, times alpha. To put that in the usual form, that's just negative RFF minus IC omega, not omega, alpha, is equal to 0. We have that equation. All right, how many variables do we have? First of all, notice that we're trying to calculate A, and in doing that, the only equations that matter are the x equations from Newton's second law. So we can get rid of this one, call this one star. We can get rid of this one and call this one 2 star. And then call this one 3 star. And if we do that, we have 3 equations, and 1, 2, 3, 4 variables. Those variables are FTWX, A, FF, and alpha. So we need one more equation as long as we don't introduce any more variables. Where's that last equation going to come from? Yep, exactly. Rolling without slipping is going to give us a relationship between the acceleration and the angular acceleration. So that says that the acceleration is equal to negative alpha r 0. And so our fourth equation says A plus alpha r is equal to 0. And if I think of this as saying alpha is equal to negative A over R, then I can just substitute that into equation 3. And it says negative RFF minus I sub C. This is a minus. We're putting a negative in there. I sub C over R times A is equal to 0. And I'll rewrite this again, divide everything by R, and you get negative FF plus IC over R squared times A is equal to 0. Um, and now we can substitute that into, so this says that FF is equal to I sub C over R squared A. Substitute this into equation 2. That's negative FTWX minus this new expression for FF minus MA is equal to minus, all these m's are little, minus little mg sine theta. Okay, so this is our new equation 2. I'll make everything positive. And then that and original equation 1 are all we have left. So that says FTWX minus big MA is equal to minus big mg sine theta. And I guess I'll multiply the second one by negative 1 and add them together. And that cancels out the FTWX's. And what we have on the left side is I sub C over R squared. This is all in parentheses. I sub C over R squared plus little m plus big M all times A is equal to the quantity big M plus little m times G sine theta. And so A is equal to the quantity big M plus little m times g sine theta over the quantity I sub c over r squared plus, I'll rearrange those, big M plus little m. Okay, so if this thing didn't have wheels, it was just sliding down the ramp without friction, and the wheels wouldn't have any mass, they wouldn't have any moment of inertia, and so this would cancel this, and you would just get an acceleration of the whole thing equal to g sine theta. And that's what you would get if you did this problem. It reduces to what you would get if you did this problem. It's just a block sliding down an incline. And if there was no body on top of the wheels, it was just a wheel rolling down the ramp. You would have the big M's would go away, and you would just have mg sine theta over I sub c over r squared plus little m, and I think that's what we got when we just did the rolling problems. It should reduce to that. And otherwise, if you put in like values that represent a disk or a sphere or whatever shape you want the wheels to be, you see that the way to make this thing go fast is to increase the mass of the top and decrease the moment of inertia and the mass of the wheel. And to make it go slow, increase the mass and moment of inertia of the wheel and decrease the mass of the top. So the only helpful advice this really gives you for the Pinewood Derby is, I said this to a couple of people last time. Well, let me draw it on here. How to cheat and get away with it. So the cross section of the Pinewood Derby wheels look like this. This is the axis of rotation. Almost the entire moment of inertia of that wheel is created by these heavy chunks of plastic at the outside. And so all you need to do is sand down those wheels, get rid of that and that. It's not very easy to see that you've done that because they're sort of tucked under the car. Reduce the moment of inertia. You've also reduced the mass a little bit, which lets you add a little more mass to the top. And good to go. Also, by the way, one thing you can do that's actually legal is you don't have to have all four wheels touching the ground. And so if you have only 3 wheels touching the ground, what you're essentially doing is taking that mass of 4m of the top and dividing it over 3 wheels instead of 2, So you have the same equation, except that everywhere it says big M, you have more mass. And energetically speaking, what you're doing is just spending less of your energy, the potential energy you start with, spinning up wheels, and spending more of it turning it into kinetic energy. Yeah. Uh huh. Right. Okay. That's all.